Welcome to the course. This course is all about robotic arms and ROS as well. But first, we are going to dig deep into basic understanding of how robotic arms works because we have to first understand that, then we can build in ROS. That is mandatory. So let's take a look how robotic arms work. Basically, there are many manipulators, and what I mean by manipulator in robotics theory is you can manipulate any object, any physical object in 3D space by a machine, a robot, without even directly touching it. So using that machine, you can manipulate its location, manipulate its mass through a manipulator. That's what it is. Most popular manipulators are robotic arms because as they are of hand shape, they are easy to manipulate things. If we connect this robotic arm on a mobile robot, it becomes a mobile manipulator. In manipulators, further, there are two major types: serial or parallel. In this course, we are just going to be dealing with serial or chain manipulators. We are not going to be dealing with parallel manipulators. Now, this circular thing or this one, these are known as joints. These are the points where actuations happen, where motors are connected, where the robot is feeling motion. These bars which connect these joints with each other, J1 and J2, are connected with link 1. These are known as links. So in a manipulator, two major things are joints and links. Okay, that's the basic concept. At the end, you can see a claw. We call it to be end effector. As it is written, through end effector, we can manipulate things. This serial manipulator, when converted with multiple serial manipulators in parallel, it will be a chain manipulator or parallel manipulator. There are multiple types of it, but we are going to be discussing only serial. Why we call it a chain manipulator? Because joints are connected with the help of links in a chain or serially. That's why it is known as this serial manipulator. Coming to the point of the basic working of these manipulator, there are two major things in its motion: the task space and the workspace. Here it is a 2 degrees of freedom manipulator, meaning only two joints are available inside of this manipulator. The dotted lines available on the screen in the first graph are basically representing the possible motion of these joints. These red dots are representing the possible motion where this end effector of our robotic arm can be in this scenario. For example, this is the current angle of theta1, joint number 1 angle, and we have drawn all of the possible values of our joint number 2 motion, which causes the which causes the motion of our end effector. So these are all the possible values when we have a constant theta1. Then these are the all possible values of theta1, not the end effector. So which is basically in some text is known as joint space, which means that all possible joints motion. Coming to the next graph, which is the second graph, which tells us all of the points that with the combination of all of the points of theta1 and theta2, the end effector can make. Okay, you can see there are huge number of points, or very with a lot of values that this end effector in xy, as it is 2 degree, only two-dimensional place will be created. So end effector can reach with the help of just two joints, sort of curves over curves over curves. This whole area is known as workspace. Workspace is a place in which your robot can reach. Okay, all possible values where your robot's end effector can reach is known as workspace. Okay, this was the first thing that we need to discuss. Now coming to the next point, which is the task space. If we see on the third graph, here we can see that there is a circle inside of our workspace, and the task specified for this problem was to draw a circular area inside of any 2D space. So obviously the robot can only draw things inside of its workspace, so that was our task space. And task space is always limited as compared to workspace, because task space is totally dependent on workspace. Task space depends upon the task, but it can only happen in your workspace. So this was the basic concept here for task space and workspace. Coming to the next point, which is very interesting and important, and it is known as kinematics. Kinematics in robotics is very important, and it is not related only to manipulators. Mobile robots and other robots as well inherit this concept. Two major types, or we should say two categories we define kinematics, are forward and inwards. Forward is the easy one. For example, we are first dealing with forward kinematics. In forward kinematics, we basically tell the angle of q1 to rotate is 0, angle of q2 to rotate is 20 degree, rotate q3 to 20 degree, and q4 to 30 degree. And then when we know these angle values, we can tell what is the effect and what is the location of end effector. So we knew angles, all of the angles, we can then tell what is the location of our end effector in x and y and theta as well. Orientation. So basically, we give the angles and we know where our end point or the tip of our hand is going to be in the XYZ. So this is forward kinematics. What we have to do, we have to provide the angles. But in real terms, what happens? We don't say that rotate your first joint to 20 degree, rotate your third joint to, let's say, 60 degree, and we might come to the point of reaching a cup that is going to be the future project of this course, or glasses or mobile phone. What we do in real term is we say reach that mobile phone, reach your glasses, make your robot move towards the cup. So this is what we do, and for that reason we use inverse kinematics. And inverse kinematics requires a forward kinematic solution. Without it, inverse kinematics is not that much efficient, or a very hard process is used if you don't use forward kinematics. So forward kinematics is going from base to the end effector. Inverse kinematics is utilizing a forward kinematics equation, and we just tell move your end effector to 2 in x, in 2 of x and 2 of y, meaning where x is equal to 2 and y is equal to 2. Adjust your angles by your algorithm and make your robot move toward that position. This is the most important interesting thing of this course, and that is inverse kinematics that we are going to be dealing with. So if we formulate it, we give the x, y of the end effector we want, and it generates angles for all of the joints. We have discussed basics of robotic arms. It's now time to use those basics and understand some higher level concepts. Coming to the first one, and that is trajectory generation. Trajectory generation, or we can include motion planning as well, in which we have a robotic arm, let's say, wow, what a drawing, and we want it to move from point A and there is a point B. Let's assume both of the points are inside of workspace of our robotic arm, and our robot can reach. This robot is going to first move to point A like this, and with the help of inverse kinematics, obviously we are just going to tell it the point A is at 4 and 4, meaning x4, y4 in your workspace. So reach that point. The robotic arm calculates forward kinematics and then inverse kinematics and make its end effector, which is this point, move to point A. Okay, robot reaches point A. Now, when we say move to point B, which is at point x of 4 but 10 of y. So robot automatically computes inverse kinematics because of algorithms and make its end effector go to this point, which is 4 and 10, 4x, 10y. But in real terms, this is a case that causes a lot of problems. Why I'm saying this? Because when we make a thing in real terms or in simulation, very real simulation that we are going to be using, forces are applied, inertias are applied on the objects, and that causes a lot of problem. For example, if I make my hand, let's say we are focusing on the tip of my finger, I move it very quickly from point A to point B. What happens? I exert a lot of forces on other things. It is not going to stop. It is not going to stop at a very specific point because it is coming with some force. So it is going to show some inertia and it is going to show some offset from the point where it needs to be stopped. To take care of this problem, in which now, as we know that robotic arms are very precise, if you move from point 1 to point B, it starts from point A and then slowly comes and stops to the point B. That is what trajectory generation is. To make the movement smooth, what we do from point A to point B, we divide these 2 points into small other points, which can be 1,000 points, on which our robot moves. Our robot end effector moves from point A to this point first, then this point, and so on and so forth, and then it starts to reach point B. As the end effector gets closer and closer to our end goal, which is point B, the robot reduces the speed, so it can never overshoot from point B, or it does not move away from point B because of inertia. That's what trajectory generation is. We produce inverse kinematic solution for 2 points, and then we find inverse kinematic solution for all of these intermediate points or steps that we call. Then we make the robot move, and we call these points to be waypoints. Okay, these points are going to make our motion very smooth from point A to point B, and that is trajectory generation. Then comes the point of motion planning, and I'm not going to be discussing motion planning or implementing it in this course because it is not of use if you don't understand the basic and practice them before going to the higher concepts. Motion planning is going to be interesting. For example, the basic concept is if I place an object from, let's say this was the intermediate point number 6 and it was 7. So point 6 and 7 are having an object in front of it. So the robot creates another path from point 6 to 7, although it was going from point A to point B. Now between these intermediate points 6 and 7, the robot creates another path and then divide it into subway points, and avoid the obstacle and still move towards point B. So that was motion planning, and it is very interesting. We will discuss that and implement it in a future course of robotic arms. Up till now, we have understood the basics of robotic arms and how they work, what are the high level concepts, and next we are going to see how we can implement in ROS and how we are going to work with robots in ROS, and all of these concepts are going to be implemented. Let's talk about the ROS version we are going to be using. Currently, we are in 2021 and we are going to be using ROS Foxy Fitzroy. And Foxy Fitzroy is an LTS, meaning long-term support has been provided to us. Now, it is going to end its support. The official developers of ROS are going to end their support for Foxy on 2023 May. So we have a lot of time to learn ROS and to implement things. Keep in mind is this end of life date. You don't need to get to the latest version of ROS as development will be lagging in the packages provided. So we are going to pick up a thing that has been developed for more than 1 year, and all of the essential packages are available to it. Now, Foxy is the thing that we are going to be using. Ubuntu 20.04 is going to be the version we are going to be using. Currently, 20.04 is installed in my system, and we are going to install Foxy on it. We can install ROS Noitic as well. ROS 1 would last version, but we are going with ROS 2 right now. So there are other options as well: Galactic, Elliptiant, Dashing, but Foxy is our choice. Coming to the point of path setup, we have our system, and in our system we have this ROS installed at this point. Okay, now ROS is installed, but the system doesn't know. There is a file known as bashrc file, mostly known as bash file. This bash file keeps the content of all the parts of your system into it. Whenever we run a terminal, it is going to be telling us that the system knows such paths. And for ROS installation, we need to tell what is the ROS2 path, what is your workspace path, and what is the package that we are accessing in our workspace for our ROS2 ecosystem. So bashrc file is going to contain all of the paths. We are going to add ROS paths and the workspace paths, and then our system will understand where ROS2 is installed. So let's take a look how we are going to do that. Let's install it on a Linux machine. Okay, ROS Foxy installation. Simple. On Google, and the first link, ROS2 documentation. One thing important here is when you're dealing with open source packages, you have to take a look on its documentation. Previously in ROS1, the documentation was not that good, but now for the ROS2, documentation is simply awesome. And the installation process is very simple. I have to just copy and paste all of the commands provided here. Okay. How fast I'm doing it is because I'm shifting between programs with Alt tab like this, and I am selecting the line, the command with the mouse and pressing Ctrl C to copy it, then shifting back to the terminal and Ctrl Shift V. In terminal, if you want to copy or paste something, it's not about Ctrl C and Ctrl V. It's Ctrl Shift C for copy, Ctrl Shift V for paste. Okay, a little bit different. I am just copy pasting things. Now let's update it. First, we have provided to put simply some links to our system where to get ROS Foxy from. Okay, and now this is the main part in which we have copied and pasted the command apt install ROS Foxy desktop and press enter. This is the point where it will install ROS Foxy, Gazebo, RWiz, and all of the required awesome packages that comes with ROS. ROS Foxy desktop is sort of a complete installation of ROS, and there is another option. We have ROS Foxy ROS base, meaning only they have mentioned it: communication libraries, massive packet command line tools, no GUI tools. But obviously we are starting right from the basics, so we need GUI tools, and we'll go with the ROS Foxy. Linking of the paths, we have to tell the system about how our system is going to find the executables to run. Okay,
environment setup, and I use the word of linking paths. So the purpose of both of these things is same, although we have to create a working space or environment, then we will link it. Okay, let's see where it's. Now once it is completed, meaning ROS is installed in your system, that's how easy it is because of the great developers. Let's exit this terminal and open a new terminal to test it. ROS2, it says command not found. Okay, ROS2 run, command not found. What is the reason? Reason is the system don't know where ROS is placed in your hard drive. Okay, this is a very serious thing you have to keep in mind every time you run it. So this is the solution for this problem: sourcing the setup script. Set up your environment by sourcing the following file. I am going to copy and paste the command source this thing, and now I'm going to try the command again, ROS2. Now sort of a warning, but that is different this time. After sourcing it with this line of code, the system now knows that there is a ROS2 command. There is a ROS2 command. It is not saying that there is no command. There is a command, but it says, tell me something more about the command. Okay. ROS2 has been installed. Now we need to step further and create workspaces for our project. What is the basic concept behind workspaces? Let's get through it. Workspace is a space that contains the structure for packages, and it carry all of the packages that you want to store in a workspace. It can be multiple workspaces in one system, or it can be one workspace with one package where you can do all of that things according to our requirement. Okay. So for example, just understand the concept of workspaces. We have a workspace here, and it contains three different packages. The first package contains a robotic arm. The second contains a mobile robot, and to some extent this is a rover robot. Then the third package, which might contain a drone. Now you see the idea here is all of these packages contain different things inside of one workspace. We can utilize other online available packages. For example, if I download this package number 3 and add it into my workspace, it comes to this point. And then I can utilize it in my project because I have that package into my workspace. So workspace contains all of your packages, all of your code is being organized inside of your workspace. Okay. Coming to the point of our custom Big Bazoo package. This package is going to contain multiple things, and obviously multiple things mean multiple directories, and all of those directories will have their own specific meaning, which will be revealed when we will be moving forward in the course. The first thing is going to be a launch file, a folder that is containing all of the launch files. Okay, this one. Then comes the meshes. Then the next one is URDF and config file and a lot of things. Config file, URDF and meshes. I'm just naming them for your easiness. Coming to the point that this resource folder and this test folder, these two folders automatically created when you will create the package. R2ARM same, the name of the package, a folder is going to be contained with the same name of the package that is going to contain all of the scripts. This has been designed specifically in ROS2 for Python modules, as we are going to be just using Python in our course. So Python modules work in this manner. So the same name of the package is going to be made, which is going to contain all of the scripts for our robot. This setup.config and setup.py file are very important. All of the paths required in this package are going to be stored inside of this setup.py file. Executable Python files are going to be stored, and the paths are going to be given inside of this setup.py file. This config file contains the description about the package. Whenever we provide package to someone else, they can explore the package through this setup.config file. Although this Big Bazoo package is going to contain these newly created subdirectories, which we will be created and using along the way. So you don't need to memorize them because they are going to get clear when we will utilize them according to the requirement. So let's take a look. Once the installation of our ROS2 is completed, we need to move toward the next step. And that step is creating our own workspace and a package inside of it. Let's take a look how we are going to do that. We are going to be using a terminal for sure for everything. I have opened up the wiki pages for these processes. All of the detail, tiny details are provided inside of these wiki pages. That's why I am showing you. The name of the workspace is going to be Robotic Arms Workspace. And that's it. mkdir, make a directory -p, meaning create a subdirectory inside of it. And the name of the directory is going to be Robotic Arm Workspace Bazoo, or Robotic Arm Workspace. That's it. The subdirectory we are going to be creating is source. Source folder is the folder that is going to contain all of the packages. Here I have Robotic Arm Workspace and a source folder inside of it. I need to source ROS2 so I can access the Colcan build. I'm going to go inside of this workspace and then the source folder and perform Colcan build. What Colcan build is going to do is create multiple folders along with the source folder. Let me show you Colcan build, and it is going to compile this workspace and form it into sort of a, I think I made a mistake here. I should have gone into the source folder. So let's get back to this folder, which is here. I'm going to delete all of these things because we need to build it in the workspace. Again, perform Colcan build, and it is going to create build, log, install folders. In source folder, there should only be packages. Now I am going to create the package that we will be using throughout the course. And let's go to this creating your ROS2 first package. I am going to be using Python. It is telling me what the structure is going to be. This is the basic command to create a package. Okay, we are in the source folder. Here we need to get to the source folder. Now we are in the source folder. I'm going to paste the command. It is going to give error because package name is not given. Package name is going to be Big Bazoo. That's what I came up with. The first package we are going to be dealing with is Big Bazoo, and the syntax is simple. ROS2 package create build type mint Python. Pressing enter, and you can see a package has been created. I am now going to perform Colcan build outside of this source folder, and let's see, it has automatically compiled. What next thing I need to do is provide a path to our workspace. Inside of our workspace, we have this install folder and this setup.sh file. This file needs to be accessed by the system to access this whole workspace, all of the packages inside of the source folder. Now, to do that, we need to do obviously the same process we did for the ROS2, but let me show you why do we need it, right? If I perform ROS2 run, and the name of the package that we created, which is Big Bazoo, and I'm pressing tab, it is not automatically completed because it does not know where this Big Bazoo package is placed. And if I source it,
inside of the install folder and setup bash. I have sourced it manually. Now if I perform ROS to run and BIG, pressing tab, it automatically completes. Now it knows where this Big Bazoo package is, although there is nothing inside of it, but sourcing is essential here. So I am going to go in my VS Code and I press Ctrl O to open up, go to home folder, pressing Ctrl H to show me hidden files as well. Here we have this bash rc file. I'm going to open it inside of my VS Code in a restricted mode. There are a lot of things and they are very sensitive things. You have to be very careful. Coming to the last portion, I have this ROS folders source in. I have this ROS sourcing command line here pasted. We don't need to do that again. This is a sourcing of my another workspace. But what I want robotic arm workspace to be sourced. So what is going to be the path? Let me create the path. Source from the home folder, robotic arm, then install and setup bash. So we need to copy whole of this and paste it here. This is my ROS1 installation source. Currently it is not source. I have commented it out because I am using ROSFoxy ROS2. And this is the workspace that I want to continuously source it. So it has been done. Let me now close the terminal that I had, save it, and close this VS Code as well. Open up the terminal again to check if this workspace has been sourced or not. ROS2 run BI, pressing tab, it automatically completes without me doing manually sourcing. So basically sourcing has been done. That's awesome. We need to now open up in our VS Code to make our life a lot easy. Open folder, home, and where was it? Robotic arm workspace, source, Big Bazoo. Add. I'm going to add this package into my VS Code so things get very easy. File managing gets easy. Creating and editing files gets a lot easier. So that is how it is going to be. One last thing before getting started is the extensions we are going to be using. The first one is ROS. This one is very essential by Microsoft because we are going to use it a lot in our simulations, in writing the code snippets, and in developing of the robot as well. So this ROS one, then the second one is ROS snippet. It is again very essential, very useful when we are typing the code. So ROS snippet, simple ROS, then code runner. Code runner is required to run Python nodes. It is not very essential as compared to other ROS one, but still we are going to be needing it. Now the next one is XML. Basic XML and XML tools. The first two, they are very essential for writing the code in XML. That is URDF, and the setting files of RViz as well are in XML. So we are installing this extension once and for all. We will explore their use cases when we are working with the files. The last one, icons. I like this one extension because VS Code icons, it creates a lot of difference when developing. You can see the folders are created inside of it and given proper icons to them. And this gives a visual easiness when working using VS Code. So that's it for now. All the things are set. Now we need to create nodes and understand how things work. So let's get started. Doesn't know what is the structure of the robot. So we have to tell by ourselves what is going to be the basic structure, how things are going to be connected within the robot structure. There are two major things when we are making a robot: joints and the links. In our case, joints are the points where motion happens. Links are the bodies that connect those joints. In this example of our robot, you can see this whole thing is known as a link. It is not producing the motion, although it is rotating, you will see, but it is a body that is connecting this point, which is rotating on the z-axis, and this point, which is further going to produce a rotation. So this blue bar is a link, and we have a red circular joint, which is going to produce the motion. So this was links and joints. Now we have the question again remaining unsolved: which point makes the robot simulation? Which link? What makes the simulation understand the structure of the robot, right? The transform is the concept which is utilized. For example, in our case, we have this circular base on which we have this bar. Now this bar is a link, circular point, the first is known as the base, which we have created, but this is what we know. The simulation doesn't know that. So transforms are utilized to produce a structure within a robot. There is going to be a difference in XYZ from base to the link number one. This is link number one, and that is going to be defined through a transform. For example, this base is on the origin, meaning origin is 0, 0, 0 in XYZ, and the base is again 0, 0, and let's say 0.1 in Z-axis, a little bit up in the Z-axis. So this point from world to base, we have a transform. Whenever we move the world, this base is also going to move with an offset of 0.1 on the Z-axis. This is known as the transform between two things. Now, whole of the robot structure is produced with the same strategy. Link number one is on the base. There is no difference in their origins, the place where they are placed. But we have this link number two, which is a joint, and it rotates along a certain axis. But it is located at a point of 0 in X, 0 in Y, and 1.2 in Z-axis. Now, this 1.2 in Z-axis is from base. Okay. This is a transform between link number one and link number two. When we move this world, base is going to be moved, and this link number two is also going to be moved because we have a specific transform, a structure in between these links and joints. So this is the basic concept of transforms, which is utilized to keep the robot in a structure. Now coming to the point of actuated and non-actuated joints. We have certain joints which are fixed, they are not moving, those are known as non-actuated. For example, this base is never going to be moved.
is never going to move. It is fixed with the world. You will see it is directly written. This joint is fixed. This link is fixed. So world and base are fixed, although there is an offset, but they are not going to move. In our case, this link number 2 here, this red circular joint is a rotational joint. It is rotating along this axis. Same goes for this one, link number 4. It is going to rotate. This link number 3 and link number 1 are fixed joints. They are not going to be actuated. Actuated means producing a motion. So link 2 and link 4 are going to be rotating. So they are actuated, and those blue bars are non-actuated. They are fixed. Coming to the last thing, parent and child. Parent and child in links and joints. These are going to create a structure for the robot to make the simulation understand what a robot looks like. Although these words are messed up, we'll see in our ways what actually they are saying. You can see there is some sort of an arrow coming from each of a point to another. Now, you can see from link number 4 to link number 3, this arrow is going outside of 4 and going inside or to a point in link number 3. This is representing that link number 3 is actually the parent and link number 4 is the child. So we have to define the structure of the robot in a parent-child relation. Similarly, we have a lot of things at this point. Base link, world, and link number 1 all are written at the same point because there is very small offset. We'll look into link number 2. Link number 2 is child because this arrow is coming out of link number 2 to link number 1. So link number 1 is parent, and for link number 1, base is parent. For base, world is parent. So that's how a structure has been created, and which gives a meaning to your robot's definition for the simulation. We'll see into the UIDF now to understand better what is happening, how the structure is being created. Let's take a look. Following a structure that we discussed in the UIDF theory portion, let's create a folder inside of our package. Right click, new folder, UIDF, Unified Robot Description Format. All of the UIDFs are going to be carried inside of this specific folder. I'm going to create a new file inside of it, bigbazoo.uidf. UIDF is the extension we are going to be using. And now we are going to develop our robots parts by parts. Okay. You are going to see an important concept of autofilling that the extensions we install are going to perform for us, and that will make our life a lot easier. We'll start with the robot. I just type ROBO. It is going to provide me a lot of things. I'll select the first one. It has automatically completed some tags and asking me for the name of the robot. I'm going to say Big Bazoo, and that's enough. The syntax is completed, but we need to define some links and joints. The first link is going to be simple link, and the name is going to be world. As we discussed, it is not going to be a fancy link. It is just going to contain the world name. It is basically origin. Okay. From now on, things are going to get complicated because we are going to create some complex things. I'm going to type LINK, and it is going to provide me a lot of options. I'm going to select link full, and you can see a lot of code has automatically been produced. This is the power of raw snippet plugin. I'm going to delete certain things that I don't need. This origin, and texture name, file, and origin of collision as well. To some extent, this is what I need currently. Although for RViz, I just need this visual tag. I don't need this collision tag nor the inertial tag, so I will leave them empty. Okay. Name of the link is going to be base link. What type of visual body it is going to be containing? It is not going to be a box. It is going to be a cylinder. Okay, and again, it automatically completes what radius and length is, the parameters of the geometry. Important point here is these are syntax followed by the UIDF, and this snippet automatically provides us with our like it's easy. I'm going to create a joint. It is going to be joint full, and again, code has been automatically produced for me. The joint name is base joint. It is going to be a revolute type and actuated type. Its origin is going to be 000. Parent link is world. Base is child link is base link. And the axes and the joint limits. Although it is not going to be a revolute, it is going to be a fixed type, so we don't need the axes, neither these limits. This is a basic structure for our first link, and you will see that how does it look like. Let me first give it a radius of 0.2 and a length of 0.05 or radius of 0.05. That would be fine. Now Control Shift P, open up the command palette, and I'm going to search ROS. In ROS, I need to select preview UIDF. It is going to generate a preview. Okay, you can see there is this small bar apparent in this whole simulation world, sort of, this preview UIDF. I am going to change the values, radius to be 0.2 and length to be 0.5. Let's see how does it looks like. It's very big. And now it is fine. So what is happening? We are making changes in the code, and what apparently it is representing is displayed with the help of this UIDF preview, an awesome extension by Microsoft. And that makes our life easy. Why it is red? Because the color is RGBA and R has been set to 1. If I change it to be 0 and set green to be 1 and save it, its value is going to change. I don't know why it is not rendered green. It changed into black, but you change these RGB values, the value of the color or value of this preview changes. Okay, Control Shift P and preview UIDF. Now there is a problem with this thing. That's why the color was not applied. It is, I deleted the material tag. Okay, now it is fine. If I make changes 0.01, save it, and you can see it has now turned green. Okay, that was interesting. Now let's create more joints and more links. I am going to paste some code that I already copied, and it is going to make a lot of sense if I save it and see the output. So in your perspective, what do you understand out of this? There is a bar and there is a ball. Is it a ball? No, it is a cylinder as well. How does it make sense? Let me show you. Link number 1 has been created. In link number 1, we have a specified geometry, and that geometry is of this length and this radius. This bar has been created. RGB, it is a blue, and A is for apparent. It is a blue bar of this length and this radius. Origin is this. Collision values are same as the visual values of the geometry. So these values are same. Initial values are randomly given. They are not accurate, by the way. So we will see how to accurately calculate the inertial values for all of the joints. Let's leave it for now. Then there is a joint. It is continuous joint. I would set it to be revolute because revolute is more appropriate for such type of robots as we need specified positions for the joints. We don't want it to be continuously rotating. Axis is what we will explore when we will be discussing always and joint state publishers. Parent is base link, the important point. Child is link number 1. And there is a offset in the XYZ. If I remove it, and now you will see the effect here in this preview, Control S, and you can see the bar move a little bit downward. If you did not see it, let me increase it with a large value, and you can see in the Z axis, proper offset has been applied to the body, to the child body from the parent. So I will undo it and apply the appropriate offset that is required. In link number 2, it is again a cylinder of this length and this radius. It is of red color, and to me this red is a little bit off, so I will set it to be 0.0 and give it a name black. Now let's get back to the point. Link number 2. Initial values are given, we will discuss them later. Visual, cylinder, radius, color, red, and length of the cylinder and radiuses are provided. Collision is the same as of the visual tag geometry. Joint is again continuous. Why I don't know, I have written joint continues again and again. Axis is what we will discuss when we will be dealing with RWIS. Parent is link number 1, child is link number 2. There is an interesting offset here, and you can play with these values and you will see the output. If I remove this 90-degree rotation, let's see what happens. The cylinder rotates to a point where it becomes useless, so I will give it a rotation of 90 degree. All of these values are properly adjusted manually by me and then proposed to you in this course. There is a limit also applied that will make sense when we will be dealing with RWIS and see its output. So basically you now understand how a URDF can make a robot, although it is not complete. I will complete in the next part how it is going to make more sense like a robot, and RWIS is going to help us understand what this purpose of this robot is going to be with the help of transforms. We partially completed our robotic arm. Now we are going to take a look on the completed form. Control Shift P, and between these videos I completed it. Preview URDF, and this is our robotic arm. Although it doesn't look like a robotic arm, but let's say it is. For educational purposes, we will consider this to be a robotic arm. One thing to note here is this is again link, this is a link, this blue bar is also a link, and we have this huge bar as well as a link. These two red dots or red cylinders are the points where rotation is going to happen. Okay, there is a problem while rendering this as well. This should be at this point as I have programmed it, but let's leave it that way and see in RWIS how things are going to be taking effect. So I'm going to close the preview. Our robot is complete. We need to launch it in RWIS. So let's create a folder, launch, and in launch folder I am going to be creating a new file name as rwis.launch.py. If you do not understand what I'm doing right now, it is from the basics of ROS2 that I taught in Ultimate Guide to ROS2 course, and I'm just creating a launch file inside of it. So let me paste the basic structure. Okay, what we have here is very interesting. We have a simple launch file in which there are some things that are imported, and then there is Python syntax followed a function, and it contains some lines and then returns these nodes to run another variable. This is a very basic structure how things work in ROS2. What I'm going to do is to make it useful. I'm going to make you understand what is happening. The first line is what makes a huge difference. It is going to first get the shared directory of R2ARM. Okay, I'm going to say package description, get the package description from a shared directory, and the name is going to be R2ARM. Okay, this is not making any sense. Let me show you what does it tells us about. So I am going to make some changes on the copied code, and then I will show what is happening. Now it is actually, if we go into our workspace and inside of the share package directory, which is very essential to understand when working with ROS2, we go into the install, then this folder of our package name folder, Big Bazoo, and here we have a share directory. Now share directory, if you open it, and then we have this Big Bazoo package here, and you can see there are certain things, but you don't understand them. Okay, what we are doing here is we access all of the package resources through the share folder in a workspace where the package is residing. Okay, so what we are trying to do, obtain that URDF placed inside of a share directory. But that is not the case here currently. The URDF file is not present. We have to make it present in the shared directory so we can access it through a global manner, not by direct path, by the name of the package. Okay. What I'm going to do is to get the code and make some changes in this setup.py file. We have not discussed anything about the setup.py file, right? We have in the theory portion. The setup.py file is going to have all of the essential paths to which the file should be copied in the share folder and how. Okay. I'm going to import some libraries, import OS, and from globe, import globe. These are going to be required to copy the folders and the file both from this package into the share folder of this Big Bazoo. In this setup.py file, we are going to write 2 lines. Here we have them. And in these 2 lines, we are doing a lot of things. First, we get to the share folder of our package that I have showed you right here, Big Bazoo. And in this share folder, name is package, and create a folder launch. Then what do? You copy all of the contents from this launch folder. Here we have just one file, rwis.launch.py, and copy and paste it to a folder that is going to be produced here. It is not currently there, okay? And again, you do the same for the URDF. In the URDF folder, copy everything and paste it in the share folder when you will be creating the URDF folder, and copy and paste all of the files. So basically copy all the files in the package into your share folder. That's what is going to happen. And let's save it and perform Colkin build to see if things are working the way I am telling you. Going into the workspace and perform Colkin build. You have to take a look on this folder. There are 2 now new folders being created because of the Colkin build. If I bring it up, launch and URDF. In launch, we have rwis.launch.py, URDF, Big Bazoo, URDF. Now, these 2 files are globally available to the ROS ecosystem. You just access them through the share folder of Big Bazoo. Okay, coming to the launch file. This URDF file is now present in the package description, which contains R2ARM. It is not R2ARM, it is Big Bazoo. Big Bazoo, share folder, Big Bazoo, UIDF, and bigbazoo.uidf. This file is now placed in the share folder, so we can access this. Okay. Now, coming to the next thing, we discussed about the transforms, joint state publisher, robot state publisher, and stuff like that. What are those? Those are basically just the nodes of packages, like the simple node we have for basic packages. We did not create nodes in this course, but these are basically simple node. Let me show you. ROS2 run, name of the package, joint state publisher .gui. This is the name of the package, and double tap joint state publisher GUI is the name of the node that is available to us. So in a launch file, if you don't know, we write all of the nodes we need to execute. They can be launch files inside of launch files as well. But there are multiple nodes that we want to execute. We write them in a launch file. We run one launch file and it executes all of the nodes. Joint state publisher, robot state publisher, these are just names, and we need to copy them and paste them here to execute them in the order that we want, and RViz node. So these three nodes are executed when we launch this launch file. So I have made changes in the launch file. By saving them, we need to perform Polk and build inside of the workspace root directory, not the source folder. So to me, everything seems to be fine. Let's launch it. ROS2 launch, and the package name Big Bazoo. Pressing double tap to show me options. RViz.launch.py. Here it is. I'm going to press enter and see what happens. It should open the GUI for the joint state publisher, robot state publisher, and RViz2. Let's take a look. So it has opened up, but things does not seem fine. The reason is fixed frame is set to be base frame, base footprint, and in our case, it is base link. But still, things are very big. Okay, it was zoomed in and it was looking like something wrong. So I have changed the fixed frame to base link, although I think it should be world because that is fixed frame for us. And you can see this has come to the right position. It was wrongly displayed in the preview UIDF. Now, these things are present automatically here because I made it changes and press Ctrl S. If you don't have these, you just have the fixed frame option, set it to world. If it is not showing, type world and it will show up in your RViz. Coming to the next thing, robot model. Go into the add and add this robot model. Then after that, press add and add this TF as well. Then this will be shown inside of your RViz workspace. And if the description topic is not represented here, so go and select this robot description to show your robot. Okay. Now, RViz opened up. The basic node don't need any explanation. Robot state publisher is there. GUI, joint state publisher is also there. But to give you an idea what actually it is doing, let me comment it out, save it, close my RViz, perform Polk and build in my workspace root folder. Changes have been saved, and it says there is an error. I don't need to comment this out. I just need to comment this from execution. Changes made, so Polk and build and launch the RViz launch file. This time GUI for the robot for the joint states is not executed. So you can see only those joints are shown which are fixed. This base one and this link one. Why does not represent a proper thing, by the way. So all of the joints which are not fixed are crumbled up on each other, which are not actuated and which are connected to the joints which are not actuated. Okay. Although the links which are basic links like link 2 and link 3 are not link number 3 is not an actuated one, but still it is not represented correctly because it is connected to a joint which is not fixed. So you can see there is a problem. We need a robot state publisher to represent the fixed joint, but we need a joint state publisher to represent the actual states and transforms for the joints. And for that purposes, we utilize this GUI thing, robot state publisher GUI, that helps us in bringing all of the current states in a dynamic manner. What I mean by that, let me show you. If you don't have this joint state publisher installed, open up a terminal, ROS sudo apt get install ROS Foxy and press tab and you will get all of the available options for the packages you can install. I am interested in joint state publisher and GUI. I press enter, provide the password, and it automatically completes. Sorry, there was a syntax error in the command, and you can see it is already installed. And if you want to install a package for ROS Foxy, you just change the name from joint state publisher and it can be installed easily. Okay, coming back to the topic. This bars are joint state publisher GUI. What they are doing, they are constantly publishing joint states for our robot in a dynamic manner. How? If I change the state of my joint number 1, you can see my robot is moving. It is actually publishing fake values for the joints by these bars. That's what the robot's joint state publisher GUI is all about. Okay, so it is working fine. Joint 1 is rotating fine. If I take a look at the joint number 2, again, joint number 2 is also rotating perfectly, but there is a problem that it passes by the body of itself as well. Now, this is the point where I want it to be. If I take a look, I don't want it to collide, so I will set the limits as well. Minus 0.25 and 3.14 is fine. Joint number 2, if I go into my UIDF, I'm now fixing the things. Okay, joint number 2, it is continuous. Let me set it to revolute. And limit is minus 0.5, 3.34. Okay, that's fine. And for the joint number 4, is it colliding? Yes, it is also colliding. Limits are 1.72 and 1.85. Joint number 4. Let me fix that. It is again continuous. Set it to revolute. 1.92, 1.92 are fine. Okay, I made changes in my UIDF, so I have to perform Polk and build. So update the new UIDF file in the share folder. Okay, now let's see if our changes are applied to our robot or not. If I take a look, yes, you can see now it is not colliding. We have changed the limits for our joints and it is not colliding with its body now. Just to make sure if our robot structure is fine or not. It is currently only dependent on the visual tag, not the collision, not the inertia. But the point of this video was to show you transforms and joint state publisher and robot state publisher. If I remove this robot model and I mark the scale for the transforms, you can see that parent and child relation for each of these things. Link number 5 is a child of link number 4, and that is child of 3, that is child of 2, that is child of 1, and that is child of base, and all of these things. In transforms, you can see tree, world, base link 1, link 2, and so on and so forth. All of the relation of parent child is represented in this transform. Frames are also represented. If you can check them out, and you can see a lot of things, get a lot of information about the UIDF structure you have, and display it in RViz2. That's awesome. It is phenomenal. It represents your whole structure of your robot, and you can examine it in an easy manner. to be very near to real world simulation for one small reason, because it produces simulation for the forces as well, and that causes a lot of problem. Now we'll jump to that discussion later. First, we need to understand this a robot. To bring it in gazebo simulation, we need to go through certain steps. The first step is Gazebo and ROS talking with each other. This is the most essential one because we want all of our systems, all of our simulation talking with ROS. Gazebo is an independent software. So Gazebo is called, then we make Gazebo and ROS talk to each other so we can have a communication with nodes, services, launch files, all of that are ROS implementation. So we need to make them talk with Gazebo. First, we perform that thing, we complete that thing. The second thing is we make this robot model to be spawned inside of Gazebo simulation. What I mean by spawn, bringing the robot inside of Gazebo with the help of ROS. So our model gets inside of Gazebo. Then we talk about the forces, the actions that I was talking about earlier. These are the most important thing when we are simulating, because now we are simulating a real world. So we need to take care of the forces acting on the robot's joints and the links. The forces are actually gravity, moment of inertia. These are the two most important forces that I'm talking about, because they are going to cause our robot's physical body take action in the simulation. Okay, you might have seen in this UIDF creation that our robot was having multiple properties like collision properties, visual properties, and moment of inertia. That inertia is what we are going to be now physically looking at, how it affects the simulation. This is a very bad example of inertia calculated for this robot. It is encompassing whole robot. That's not fine. So we will look into how to first calculate inertia for our joints, links, and then we will apply it onto our robot, which is going to affect the simulation. And you will see if we perform the friction damping and we don't care about the forces, our robot is going to collapse. Then we will talk about the controllers to make this robot looks like it is in a simulation in a very stiff manner. So we need to first understand the forces and we need to take care of those forces by calculating proper values for inertia and masses for the joints. So let's take a look. Ours was exciting. Now Gazebo, which is more exciting and more interesting because it deals with physical properties and very close to real world simulation. We are first going to set the pipeline of launching Gazebo. Okay, I will explain you how things work in that. We are going to create a new file in the launch folder, gazebo.launch.py, same as we did with the RViz. I'm going to bring in the contents that I've already copied and save it. Let's take a look what they are saying. First, some important and required things, the imports and the libraries we need. In the generate launch file description, we obtain the package and then the UIDF file from the share folder of our package. Okay, you need to understand this convention that accessing the share folder and accessing the files from the share folder. That was not happening in ROS one. That's why I'm emphasizing on it. In the launch description, we have utilized a different approach this time. We have not given names to the nodes and executional processes. We directly give the nodes and the execution processes directly to the launch description as an parts of an array. Now, the first thing is execute process. It actually executes a command. Gazebo minus its lib gazebo ROS factory.so. If we open up a terminal and write this command, it is going to execute it and open up Gazebo. This basically deals with the communication between Gazebo and ROS. So it initializes that communication that we need for ROS ecosystem and Gazebo ecosystem. We need to make them communicate. Okay, so lib gazebo ROS factory.so is going to do the thing. The execute process is actually executing this command. It's like executing this command in the terminal. So we have pasted here and it automatically executes when we run the launch file. After that, we have a package Gazebo ROS in which we are executing depreciated syntax, sorry, executable, which is a node spawn entity. When Gazebo is opened up and we need a robot to be spawned inside of it, that's the point where we require spawn entity, which spawns a robot into Gazebo. Let me show you what is actually happening. If I copy this command or if I write it, let me copy the big one, Gazebo -s and libgazebo ROS.so. Let me press enter and see what happens. ROS was initialized without arguments and things are working. Let me see ROS topic, ROS to topic list, and we have ROS running. So Gazebo is here. Now the next thing we need is, let's take a look, spawning the robot. So ROS to run spawn entity Gazebo ROS, name of the package, and then the spawn entity node. Inside of it there are some arguments. Entity name of the entity is Big Bazoo, and then there is a file as well, -b -file, and the path to the UIDF. Let me directly copy the whole path and paste it, and let's press enter and see what happens. I don't know what is going to happen, and yes, there is an error. So I think the B thing is not working. Oh, there was a space in the file as well. So it says spawn perfectly, and you can see the robot has been spawned. If I delete this robot and perform the command again, our robot is here. It has been automatically spawned inside of Gazebo. So the first command I wanted to show you is running ROS and Gazebo and communicating with each other. The second node is actually spawning the robot inside of Gazebo simulation, as you saw. Now the next thing is providing the robot state publisher. This is not very essential right now, but we will be running it so Gazebo does not cause any problems with the states of our robot. You might be thinking of where is the joint state publisher GUI. Joint state publisher GUI is not going to be utilized now because we don't want fake joints for our robots, and we are going to be publishing real values for the joints to make our robot move accordingly, according to our requirements, and that is going to be done using the controllers that we will talk later in the next section. But for now, our robot is here in the simulation. It has been spawned perfectly. The thing that matters to us is the physical properties that I discussed. So in the view drop down, we are going to see a lot of options. We are directly going to go collision, and collision does not provide us any valuable thing. So let's uncheck it and go to contacts, where the robot is contacting with the ground. Currently is shown. There is also a problem related to that inertia, the main thing, and that causes a lot of problems when working with robots. And one interesting thing here is this last link is continuously floating and it is not acting like a real life, although we have not provided any joint movement command, and it is moving continuously. It is also a problem. Now this big pink bar, which is representing inertia for that moving bar, and you can see it should be just as small, or it should be of as the size of the cylinder. But it is a huge box. This is a huge problem. Wrongly calculated inertial values, and that can cause serious problems when we are working with a robotic arm. You can see the perfectly fine calculated inertia is this one, which is a box, and it is encapsulating the link number 1. But for the link number 5, things are very bad. In the next video, we will take a look how to calculate inertia for geometry, cylinder geometries, and implement mathematically in our robot. Let's take a look.
Giving you a link. That is from Ross Wiki, which gives us information about how you can fill up the collision properties of your URDF and the inertial properties. So in order to get your model simulate properly, you need to define physical properties for you. That is physics engine properties that a physics engine and gazebo would be needing, and that comes with inertia. The element is also a sub-element. Why I'm reading in front of you, I don't know why, but this is important thing. It doesn't seem to be important because it is very relevant for robotics, but for simulation we have to understand this. So the thing that we are understanding is inertia matrix is a 3x3 matrix which has 6 elements, and the most important one are IXX, IYY, and IZZ. Okay, we can find how to calculate inertia tensors here, or if we have meshes, we can use MeshLab. So we are going to be using inertia metrics to list of moment of inertia tensors. So now what we are going to do is to apply some of the mathematical formulas that I don't want to write on the theoretical portion because they are already written. In the inertia physical properties, they are utilizing the same case as of ours. They are using cylinder, and we are also dealing with cylinders, all on robotic arm. They have calculated their inertia values, and with what formula they have done that, let's find out. They have provided the list of moment of inertia tensors that we have to look into. You can read all of that in your free time after this lecture. So there are a lot of equations provided to us to calculate moment of inertia on this Wikipedia page, list of moment of inertia. We are going to go into the section where we are going to find list of 3D inertia tensors because Ross accepts in the form of tensors. It requires 6 different values. Important one are these 3. So in our case, we are going to go with solid cylinder with radius r and height h and mass m. Now mass is an arbitrary thing that we can give, although we give the height and the radius as well. In this case, height is h in the form of length that we give to our radius, and r is simply the radius. We need to apply this formula, and this is ixx, this is iyy, this is izz. So this might be ixy, ixz, and so on and so forth. So we don't care about that, we just care about these 3 things. Let's solve it. For the example, we have 3r square plus h square, and in this case, h is equal to 0.6, r is equal to 0.2. Okay, I'm going to bring it into this page and then solve it. Okay, let's open up calculator. 3r square, r is 0.2, and I want 3 into 3 multiplied by r square. R is 0.2 square, and then add it with h square, which is 0.6 square. 3r square plus h square. That's fine. And we will then multiply it with the mass. They have given the mass of 10, so multiply it with the mass of 10, 4.8. We are now going to divide it with 12. I'm applying this equation right here, 0.4. So let's say 0.4 x, 0.4 y. Let's take a look. They have given ixx 0.4, iyy 0.4. So our understanding of the application of equations is correct. 0.2. Why izz is 0.2? Because the formula is different. Let's apply it on our system. Mr square. It's 0.2 square, and that is multiplied by 10. Then that is divided by 5. Sorry, it was not divided by 5. It was divided by 2. So answer is 0.2. So we are looking at the correct equation. This was just a check. In the next video, we are going to apply this formula to all of our joints, and let's see what happens. to implement those practice into a robot, right? So all of our parts for the robot were made from cylinder, right? And that was intentionally done to make things easy for us. Now we have to apply this inertial metrics to our robot, each and every single part of it. If we open up our bigbazoo.uidf, and let's start from the first base link. And base link is a cylinder of this and this radius in length. We need to write the equation here as well. 1 by 12 into m, and that is going to be multiplied by